All right, we're ready to continue, guys. Guys, we're gonna get started with part 2. All right. So those of you who are still staying, I applaud the bravery because we're gonna look at a lot of math. Hey guys, so I don't know if it'll help if you have a paper to kind of follow the steps that I'm gonna derive maybe. So I'm actually gonna kind of squeeze in a lot of dense material in the next 2 slides. It's basically gonna be entire quantum mechanics in 2 slides. You can in fact you can derive everything in quantum mechanics from what you're gonna see in the next 2 slides. So it's quite a dense material. So how does quantum mechanics describe nature? It describes in this kind of a psi notation, which I said is direct Ket notation, and that state vector lives in this abstract vector space that we call Hilbert space. And you can kind of think of it as, for our purposes, is a linear vector space with inner product. So inner product is the same as the dot product that you might have learned in linear algebra or some other courses. And the state is normalized, which means it's a unit vector, so or its L2 norm is equal to 1. That actually exists so that we can preserve the total probability to be 1. And this is something called Schrödinger's equation, which describes the temporal evolution of quantum state. It's like a fancy way of saying how does quantum state evolve. And you see it on the left side, you see the time derivative of the state is kind of affected by what's on the other side, which you see as h. That's something called Hamiltonian. You might, if you have studied some classical mechanics, maybe you've studied Lagrangian mechanics, Hamiltonian mechanics. That Hamiltonian is exactly the same as the Hamiltonian in Hamiltonian mechanics. So it basically correlates with the total energy of a system. So if you look at what it says, it just basically says, rate of change of the state is kind of, affected by the total energy. That's basically what Schrödinger equation says. You can ignore the I and h bar. Those are just constants. So not really important. And important thing to also note is that it's the linear differential equation, which means that if psi1 and psi2 are solutions to the equation, the sum of the two is also a valid solution, which kind of reflects the property of superposition, that 2 states can exist at the same time and still be valid. And how do you create a multi-particle system is that, let's say you have qubit 1 and qubit 2, how do you combine them together? You take tensor products between the 2 Hilbert spaces. And, in case, let's see on the right, we see phi I and phi j. Phi I could be from H1 and phi j could be in H2. We take outer products or inner. By the way, how many of you have taken linear algebra? I hope I'm not losing too many of you. How much sense does it make? Like, raise your hand if you understand what I've been saying so far. Oh God, okay. All right, some other results later we're gonna see will be understandable. It's not gonna be cumulative. So if you stick around, hopefully you'll get something more out of it. Okay, so what you see here as tensor product of 2 states, this is something called separable states because that represents independent states. So independent 2 qubits that have no correlation with each other. But the generalized state must be represented as an entangled state, which doesn't have to be separable. And we're also going to talk about measurement because I mentioned, measurement is kind of weird in quantum mechanics, but really haven't, justified anything about it. So in quantum mechanics, a measurement or any kind of observable quantity like energy, position, momentum, magnetic moment, whatever it is, it has a corresponding operator called, here as an example is an A. And it is self-adjoint. And if you study linear algebra, you probably know spectral theorem says that it has, for n by n matrix operator, has n number of eigenvectors and eigenvalues associated with it. And that's the eigenvalue equation you see up there. In fact, these eigenvectors or eigenfunctions, depending on the space you're dealing with, is complete. So as in, it forms a complete orthonormal basis. So you can pick any arbitrary state psi, and you can express this linear combination of these basis states, where CIs you see are just any kind of complex numbers. And to what are these CIs? Born rule describes it as if you make a measurement on it, the probability of observing the state AI is equal to CI modulus squared. So that's why you actually saw earlier 1 over square root of 2 is because you square that number and that becomes half. Does it kind of make sense? Because that's 50% plus 50%, so total probability is 1. Yeah. Okay, so there are actually 3 kind of a prevalent kind of a interpretations of measurement in quantum mechanics. Copenhagen interpretation is the kind of a most widely accepted one. It says the physical systems do not have any definite properties until measurement is made, but it really doesn't define, what constitutes measurement. It's kind of really vague theory. So von Neumann interpretation actually tries to address that by saying everything, including the measurement process, must be expressed in a quantum mechanical way. But however, there's like a really bad philosophical issues with this interpretation, because it brings in concept of consciousness into the measurement, and that's like almost, nobody's really able to answer that question really. So, the last one is Many Worlds interpretation of quantum mechanics. It says wave functions, or in any kind of state, doesn't really collapse, or the state that superposition really doesn't break when you make a measurement. It says, in fact, whenever a measurement is made, or whenever there's a superposition and measurement is made, equal copy of the universe is created, where each universe is unable to access to each other. So this is kind of you can't really falsify this claim, which is why some physicists kind of buy it, but most physicists kind of stick with the Copenhagen interpretation. So let's look at the Schrodinger equation in one dimension, just kind of get a sense of what really the psi thing we've been talking about is, because we kind of treat it as an abstract thing, and it's still going to be abstract, but I want to kind of hope you to get something, get some understanding of it. I'll argue that psi must be complex, because we're going to prove it by assuming the psi is real. If psi is real, then the left side is complex because of the I term, and the right side is real because there's nothing complex on the right side. So by contradiction, psi must be complex. There's also interesting about the dimension of this state, because I don't know if you've studied linear functional analysis, but inner product of 2 functions, it means you integrate the conjugate in itself throughout the entire space. It must be 1 because we talked about the normalization condition earlier. So we have this equation where we have the unit of psi squared times distance is equal to 1. 1 is dimensionless, so unit of psi must be 1 over square root of length. Yeah, I really don't know what it means. I don't think nobody does. I don't know. Yeah, but it's kind of interesting because this wave of probability has unit of 1 over square root of length. What does that mean? I don't know. So, how can we really mathematically manipulate these things? These are kind of abstract. Well, let's take a look at how our regular computers work. They work by, we have bits. We run them through these logic gates to perform interesting computation. And with these kind of gates, we can start building interesting kind of circuits. In fact, any Turing computable function can be converted into this kind of following form, where any arbitrary logic circuit can take n number of bits and output m number of bits. In this example here, you see on the photo is n is 3 and m is 1, because it takes in 3 bits and outputs 1 bit. And of course, there's universality. If you're familiar with NAND gate and fan-out, can represent any kind of arbitrary logic circuits. So I want to kind of give you an intuition of how quantum gate works. Because in classical logic gates, we said it just takes n number of bits and outputs m number of bits. And what quantum gate takes is it takes an arbitrary qubit. In fact, if the notation is not familiar, I wrote 0, 1, 0, 0, and I put everything inside the ket. That's a simplified notation of the tensor products states. So what really happens when you put it inside the gate is that the gate has an associated evolution operator, and that kind of acts on the state for a finite amount of time according to the Schrodinger equation. So if you're familiar, I don't know how many of you actually know quantum mechanics, like to any degree? Studied it? Okay, that's fine. So for those of you who have knowledge, it's the rotation of Bloch sphere. That's what it really does. And in fact, when you actually feed, instead of just a pure state, like pure 0, 1, 0, 0, if you feed in superposition of states, in fact, this gate will act on all of them simultaneously. That's where earlier we talked about quantum parallelism, about being able to traverse maze through all possible paths simultaneously. That's what it really comes from. Because you can treat the input as an arbitrary state vector psi, and if a psi has n number of qubits here, in which case, in this case, n is 3. So all possible combinations are 2 to the 3 equals 8. So for arbitrary n number of qubit system, if you pass it through a quantum gate, it acts on all 2 to the n basis states. So you're able to perform kind of an exponential amount of computation at the same time. So qubit kind of, qubit, it really is a linear combination of 0 and 1, and that really is not surprising because that's what we've been saying so far, right? Qubit is a superposition of 0 and 1. Yes?
But like electrically, how does that work where you can like have several gates at once? Like you go back to the slide.
Sorry?
Like I don't understand like electrically like how you would make something like that for a gate.
So yeah, the way we build gates currently, right? If, for example, let's say NOT gate, we have like MOSFET, resistors, and whatever, right? We're not going to discuss specific implementations. We're going to just treat it as an abstract device at the logic gate level. Is that okay? Well, we're going to kind of get to it at the end. I might mention how to actually build a quantum computer. We'll get there, okay? All right. So yeah, qubit really is a superposition of 0 and 1, and the Hilbert space must be isomorphic to a two-dimensional complex vector space because we said alpha and beta are complex numbers, and the normalization condition just follows as what we talked about before. Because if you want the side to be a unit vector, the modulus of the two coefficients must add up to 1. So here are some examples of quantum gates. There are actually a lot more gates than these, but we're only going to talk about 3 of them today. X, Z, and H. X is an X gate. Same as kind of like a NOT gate in our regular circuits. So if you act X on 0, it's going to output 1. If X acts on 1, it's going to output 0. Z gate is like something called phase gate. If it takes in 0, it just outputs 0. If it takes 1, it's going to add that negative phase on top of it. The last is Hadamard gate. It's like a gate that creates superposition. So if it takes 0, it creates an equal superposition of 0 and 1. You see 1 over square root of 2 factor. So if you square that, it's half. That's why it's like equal superposition. If you put 1 into Hadamard gate, it's outputs the same thing except there's a negative phase on top of it. So now with everything that we've talked about, we can talk about teleportation and how it really, really works. So before we go ahead, we have to talk about these 4 states up there: psi plus, psi minus, phi plus, phi minus. These are just a set of entangled states. These are called Bell basis states. And in fact, the 4 of those together form complete basis. Here we see I don't know if I can, hold on. There it is. So the psi here you see, the big psi you see is the state that represents the entire system. So remember we had a qubit that Alice wants to teleport a qubit to Bob's lab, and Alice has that qubit, and Alice and Bob also shares an entangled pair. In our case, it's going to be psi minus. Excuse me. And psi minus, as written up there, is going to be 0, 1, minus 1, 0, which is represented here on the right side. And the left side is the state of the qubit that Alice wants to teleport. So it's written really like a general state, alpha 0 plus beta 1. And if you actually kind of massage the term out, you get this form at the end where you can represent this entire system as combination of a Bell-based state, which are represented above. So let's kind of think about this together. So that means you see that this terms above at the front represents the qubit that Bob has. So if I make a measurement, if Alice makes a measurement on her pair of qubits, she's going to get either psi minus, psi plus, or phi plus, or phi minus. That kind of instantaneously affect the state of the qubit that Bob has. It's going to be either of the 4. One of the 4, or one of the 4 of these with 25% probability each. So in a way, with 25% chance, Alice actually teleported. Alice transmitted information instantaneously, faster than the speed of light. But that, of course, 25% really you can't really trust on it. So what Alice actually has to do is to transmit 2 bits of classical information. So if let's say she measured psi minus, actually that's too easy. If you measure psi plus, right, you want Bob to have alpha 0 plus beta 1. And what so you can see that earlier we talked about X and Z gates. So what Alice does is tells Bob through some kind of classical channel what kind of gates to apply. Then Bob will go in and apply XZ or ZX or something, a combination of the 2, to be able to retrieve the original qubit. So, at the end of the day, you really can't transfer information faster than the speed of light, but with 25% probability, you can. This is kind of interesting. Okay, so we kind of have been talking about, teleportation, some kind of a formalisms, But I kind of want to give it like a really basic, at least some basic. This is the most as basic as it can get. This is the most like a simple problem that you can talk about in quantum mechanics, in quantum computing. Sorry. So this is called Deutsch-Josza algorithm, and it involves an oracle, which is a function that takes in n number of bits, binary string, and outputs either 0 or 1. We're only going to talk about a case where n is equal to 1 because that's the simplest case. So the question is f balanced or constant? So what is it? Let me just clarify. If f is constant, it's always going to output the same number regardless of the inputs. For example, in our case, I kind of wrote down like a kind of something that looks like a truth table that writes down all possibilities, all possible f functions, which are f0, 1, 2, 3. So in our case, f0 and f3 are constant because no matter what the input is, it always outputs the same number. Right? And if it is not constant, we're going to call it balanced. So let's say we don't know what really f is, but we at least know this is the property of the f. The question is, can we tell if f is constant or balanced? So if we have a classical computer, how many queries would you need to check if it is balanced or constant? How many? Shout it out. 2. 2, yes, right. Well, why? Right, so you'll check the both, right, exactly. You'll be able to just match it immediately to the truth table here. You'll be able to tell whether it's constant or balanced. In fact, well, what I'm going to argue is that for a quantum computer, it only takes 1 query, in fact. That's a good improvement here. And that's going to involve this gate we've never talked about is something called, we're going to call this called oracle gate. And it's going to take 2 qubits, and it's going to take x and y. It's going to output x and y, x or f of x, where f is the oracle function. So I kind of warned you it's going to be a little dense, but this is the most simple example I can give you in quantum computing. So hopefully, you can follow along. So I'm going to go through step by step how this works. So in our case, n is equal to 1. So you see the n, like the tensor n symbol, that's just h, nothing else on top of it. So we have 0, 1 to begin with, and we apply h to both of them, which gives us 1 over square root to 0 plus 1, and the other with the negative symbol after applying Hadamard gate. And then we apply the oracle gate. You can kind of see, because earlier we talked about the property of quantum gates. If you feed in the superposition, the gate will apply to every single basis vector. So you kind of see by linearity, all the components having applied the U of F gate. And then you kind of massage the term, reorganize the term to look at, kind of make it look that way. I'm kind of poorly describing this, but there's really not much else I can say about this process. And you can ignore the second qubit, in fact, after this process. So you can see I ignore the second term. And then you apply the Hadamard gate to the first gate, which gives us this superposition. And that's basically it. And then after you reorganize the term, what you really notice is that, so if f of 0, x or f of 1 is 0, is f balanced or constant? If f of 0, x or f of 1 is 0, is it balanced or constant? Constant? Yeah, that's right. It's constant. So that's exactly why if we measure 0, so after performing all the computation, we're going to measure the first qubit. And if first qubit outputs 0, then f is constant, and it's going to be balanced otherwise. Because you see that this term will either, 1 will be 0 and 1 will be 1, based on whether f is constant or balanced. So this is really this kind of this is an artificial example. It's kind of like a guinea pig. This is, in fact, the first example that was published that shows quantum computers can be faster than classical computers. Because with a classical computer, you really can't get better than 2 queries, because that's all you can do. Because with 1 query, you know nothing about the oracle function. So that's one example. The other example is finding needle in a haystack. You can kind of think of it. So how do you solve the problem? You really try to bring a magnet to it. And that's what quantum computer kind of does. The kind of the details of this algorithm is kind of really beyond the scope of this talk, because the Deutsch-Josza algorithm was like the most simple quantum algorithm there is. But I can give you the quantum circuit for it. And if you imagine a problem of finding an element in an unsorted array, the best you can do is n steps, because you have to really go through the entire array to be able to find the element you're trying to find. But a quantum computer can do it in square root of n steps. So in fact, quantum computer benefits this from all kind of search problems. Like any kind of NP complete problems, quantum computer can get quadratic boost or this kind of a square root of boost factor. So if it is a million, let's say n is a million, for a classical computer, it's going to take 1,000,000 steps. For a quantum computer, it's only going to take 1,000 steps. It's not really significant because for problems in NP, it's still going to be exponential. But when the size of the problem grows, square root factor can be still kind of be significant. So we've kind of been treating qubit as an abstract device. But how do we actually build a qubit in a laboratory? So we're going to look at a very simple system, a hydrogen atom. Hydrogen atom consists of a proton and an electron. And what we can say is that we can encode qubit as at the state of the electron, where the ground state of the electron can represent 0, and the first excited state of the electron can represent state 1. And an arbitrary state is in a superposition of the two, ground state and the first excited state, both simultaneously. And we're going to model it as a problem, something called particle in a box. If you think about the motion of an electron in a hydrogen atom, it's not really this is a one-dimensional case. You can kind of think of this one end of the box as like the kind of a center of the hydrogen atom, and the L as like the kind of something like a Bohr radius if you studied chemistry or physics. But really, this is kind of a rough model. It's a really kind of poor model, but it gets the order of magnitude right. So I wanted to use kind of this example to show you how you would realize it and how you'd be able to control a qubit. So we need to go back to the Schrodinger equation. And if you studied like a basic differential equation, you would notice that the general solution for this differential equation takes the following form, where the psi of 0 is the initial state. And from the general state, we said, without kind of a loss of generality, what we can say is that initial state is always a superposition of arbitrary base states, which is what's written in the second line. And if we plug the second line into the first line, we get the general solution to the Schrodinger equation in any problem, as long as the Hamiltonian is time independent, which we haven't discussed, but it's another topic for other talk. I won't actually derive the answer, but I will tell you what the answer is. This eigenbasis turned out to take the following form: square root over L sine of n pi L over x is in fact it's a standing wave solution. If you think about how do you represent a particle in a box as a wave, it kind of needs to be a standing wave, and you will notice that no matter what the value of n is, it's going to be a standing wave. If you put in n, it's like a one kind of a long wave. If you put n, it's two. It has like it kind of a squiggles once, and you keep adding node as n keeps increasing. And we only we're interested in 0 and 1 states because that's how we're going to encode qubits. So these are the eigenstates and the eigenvalues associated with it. The E's actually turn out to be energies because H is an observable, as I mentioned earlier, for energy. So when psi equals 0, we can say it's without loss of generality. We can represent psi of 0 as a superposition of 0 and 1, where alpha and beta are unknown constants. And we can, going back to our general solution, we can plug in that form and we get the second line. And we can kind of factor out e to the power of the E1 term. And we get this, where in the right side on the 1 term, we see the delta E. And delta E actually turns out to be about 10 electron volt. Converted to frequency, it's about kind of close to the frequency of visible light. And this is kind of my way of hinting how if you were to have a qubit made out of hydrogen, you would in fact shine visible lights at it to control it. That's in fact how it is achieved in some laboratories. And state of the art, we're kind of getting close to the end of the talk. So hydrogen atom, it's kind of simple, nice to deal with, but really can't scale that. So how do research laboratories really build quantum computers? There are kind of two most prominent methods. One is a trapped atomic ions. What you do is you trap a bunch of ions, literally just a trap bunch of ions, and you shine lasers at them to control them individually. And the other is superconducting loops. If you have maybe electrical engineering background, you might know Josephson junctions. That like a superconducting loop has a nice quantum property. Most likely, trapped ions are going to be used for memory, and superconducting loops will be used for like processing for like something like CPU, because trapped ions can hold quantum information for a very long period of time, as opposed to superconducting loops. Their qubit information is lost very quickly because they really easily interact with the environment. So kind of this measurement is made, and it loses superposition. But superconducting loops can be kind of a mass manufactured, which is kind of a really strength it has. But trapped ion, it has to be manually engineered, every single one of them. So it's really hard to mass produce. So that's kind of it. If you have any questions, feel free to ask now. Yes. How long?
How long do you think quantum computers will have?
That's a really kind of a controversial, kind of a debated topic. I think it's going to take at least 3 to 4 decades. So, we don't know quantum computers as opposed to states. Thanks for coming, guys.